Part number 3, welcome back. We're going to combine what we did in 01 hash and 02 transaction to create a Merkle tree. So a Merkle tree looks like this. It's a binary tree and all its children are, in our case, transaction. So we're going to create a Merkle tree from transactions, and we're going to build a Merkle tree in the following way. Each transaction, we're going to take its hash. So transaction 1 will be hash 1, transaction 2 will be hash 2, etc., etc. And then we're going to take each leaf and combine them and create a new hash from them. So we're going to concatenate, in this case, hash 1 and hash 2. So we're going to have hash 1, 2 and create a new hash from it. Okay? And we're going to do that for each height in the binary tree. So here, for example, we're going to combine hash 5, 6 and hash 7, 8 to get hash 5, 6, 7, 8. And then we're going to hash it one more time. So in the end, we're going to concatenate hash 1, 2, 3, 4 with 5, 6, 7, 8 to get hash 1, 2, 3, 4, 5, 6, 7, 8. And then we're going to hash it again. Okay? And this will going to give us some benefits. So if we want to prove if transaction 1 is in the Merkle tree, we only need transaction 2, hash 3, 4, hash 5, 6, 7, 8, and then we're going to check if we're going to get the actual root of the Merkle tree. So this is the main benefit. To check if one transaction is in the Merkle tree, we're going to take one element from each height and combine them in the right way to check if the root of the tree is correct. And now we don't need each transaction. So we save a lot of bandwidth, a lot of computation. We don't need to hash every transaction. We only need to hash one element from each height. And this is our implementation. We have the class Merkle tree, and this takes in a list of transactions, and then we're going to build up this data structure, this binary tree, from the bottom to the top. So in the first step, we're going to create a new dictionary called MT, and we're going to create all the leaves. So we're going to create a new list of all the hashes from each transaction, and we set the first height, so height 1 of the Merkle tree, to our leaves. So this leaves contains all the hashes of each transaction. And then we're going to call Merkle, and Merkle takes in the leaves that we just created, and Merkle will, in a for loop, will create all the rest of the Merkle tree, all the rest of the binary tree. So while length of leaves is greater than 1, here we check if the leaves is not the root node. If it's not, we're going to continue. And we iterate over each leaf, get the leaf that's on the left and get the leaf that's on the right. And then we append the left leaf to the right leaf and calculate a new hash. And this we're going to append to the parents. And if we do that for one height, we set the leaves equal to the parents and set the correct height in the Merkle tree to the parents. And then we empty the parents array and do the same thing until we reach the root node. And then we have this data structure. We also define some properties. So the root node is the root node of the Merkle tree. Two Merkle trees are equal if the root node is equal. The length of the Merkle tree is the height of the Merkle tree. GetItem returns all the hashes in the height k. And then we have the string method, which just prints out the Merkle tree in a nice way. We also define a random transactions method, which just returns a number of random transactions. So here, for example, we can create 2 random transactions, but we could also do 4 or any number that we want. So we're going to use that to create 8 random transactions and initialize a new Merkle tree. And if we print out this Merkle tree, we're gonna see that we have a height of 4, exactly like the example that I showed before. And this is actually the hash of the first transaction, this is the hash of the second transaction, and so on. And height 2, so this hash is, if we take this hash and this hash and concatenate it, so we do this, left plus right, and we take its hash, we're gonna get this. And this we do iteratively until we reach the root node. If we assert that the Merkle tree has a height of 4, it's true. And of course, we can look at the root node of the Merkle tree and look at its hash. And it's, of course, the one from height 4. So the interesting thing is, of course, if we change anything in the Merkle tree, if we change any value in the Merkle tree, if we change any transaction in the Merkle tree, we get another root node. And if we have another root node, we have a new Merkle tree. We have a different Merkle tree. So if we go and change the transaction 2 value to 500 and create a new Merkle tree, what we will get is a new root hash. So this hash is different from this hash. But actually, if you look at the transaction hashes, they are all the same. So the 8th one, so this one is equal to this one. This one is equal to this one. The only transaction that changed is actually the third one. So the third hash is not equal to this one. It changed. And because one transaction changed, the whole Merkle tree changed as well. Because every transaction influences the root node at the top. And this is why this root node is different from this. So if we assert this, the Merkle tree is not equal to the changed Merkle tree, it's correct. What's also interesting, of course, is what we call a Merkle proof. If I want to check if a transaction is actually included in the Merkle tree, this check is called a Merkle proof. And we're going to implement it in the following way. So, for example, if I want to check if the transaction 1 is included, I need the transaction 2, I need this hash, and I need this hash. And then I'm going to check if the root node that we just calculated is actually equal to the root node from our Merkle tree. And this is what we're going to implement in the proof method. So the proof method takes in a Merkle tree, a transaction, and a Merkle branch. And a Merkle branch are all the nodes that we need to validate if the transaction is actually included in a specific Merkle tree. So if we want to check if transaction 1 is included in this Merkle tree, the corresponding Merkle branch would include the hash of transaction 2, hash 34, and hash 5678. And then what we're going to do is we're going to take the transaction 1, hash it, concatenate this hash with hash 2, then we're going to get hash 1, 2. We're going to hash that one more time, concatenate that with hash 3, 4, and then we have hash 1, 2, 3, 4, and then we're going to concatenate 1, 2, 3, 4 with hash 5, 6, 7, 8, and hash that one more time, the result, and then we should get the same Merkle root that we have from our original Merkle tree. And this logic is implemented in the proof method. You can go into the implementation details if you want, but I'm gonna skip this. So, for example, if I have the transaction 0 and I want to check if it's included in the Merkle tree, and we have the Merkle branch 1, 1, 1. What does that mean? So, for example, if I have this Merkle branch, this stands for the following. Take node 5 from height 0, take node 3 from height 1, take node 0 from height 2, and so on until you reach the root node. And this is exactly what 111 stands for. So 111 would be, in this case, would be second hash from height 1, the second hash from height 2, the second hash from height 3, and then of course we have the root node. So It's the second root because, of course, our list is 0 indexed. So we start with 0. So this runs. And then we can do the same for transaction 1. And in this case, of course, the Merkle branch is different. So now we get our Merkle branch is 0, 1, 1, because if we check for transaction 2, we need this hash. So from height 1, take the first one, and then the Merkle branch is actually the same. So we still need hash 3, 4 and hash 5, 6, 7. And if we run this, it works as well. And in the end, we have another example for transaction 4. So transaction 4 would be, in this case, this one, the 5th transaction. And here we need hash 6, hash 7, 8, hash 1, 2, 3, 4. So we have the 5th transaction from the first height, the 4th hash from the second height, and the first hash, so in this case would be this. So if we run this, it works as well. But of course, if we change the Merkle branch to something that's not correct, so if I say take this Merkle branch, this of course will fail because this is not a correct Merkle branch. So I hope you got the main idea of Merkle branches. They are used everywhere. So for example, if you look into Ethereum, there are actually several Merkle trees that are stored in each block header. And we're going to talk about block headers in 0.5. So there are a lot of use cases for this in crypto. We're going to use that for our block header that we're going to implement in 0.5, where we'll actually not store all the transactions in the block header, but we're going to store the root node of a Merkle tree that we're going to create from all the transactions. And then this block header we're going to use for mining, but this we'll get into in 0.6. So I hope you got the main idea of Merkle trees. And the next one, we're going to talk about wallets. So see you then. Bye bye.